Hello and good morning. Let us start today's lecture by giving one example. So far, we have discussed the degenerate perturbation theory, and now we are explicitly going to discuss two different examples, one of which I had unofficially discussed in the class. Where I have said something about nearly degenerate systems. But now we are going to look at the same example but with exactly degenerate values and the number of degeneracy. It's a twofold degeneracy in the system. So, as an example, so this is our 8th lecture, and as an example we are going to discuss twofold degeneracy. We have already discussed such, but now what we are going to do is that we are going to discuss it and then we are going to generalize it. So what do I mean by twofold degeneracy? By now it's already known to you. We have the unperturbed Hamiltonian, which acts on m0, and then this gives you the value E0 kate m0. That's one state. And now if you have the same Hamiltonian, unperturbed Hamiltonian, operating on kate n0, giving you the same value of the energy and the state back, with of course the orthonormality criteria, this is equal to 0, and we have assumed that these states are normalized. And as already said, any linear combination of these states is still an eigenstate of H0. So this is the first statement that I wanted to make, that we have the unperturbed Hamiltonian which acts on some state m0, and it gives us the energy eigenvalue to be E0, and then acting on a different state, it gives us the same energy eigenvalue. And then we have shown that any linear combination of these states kate m0 and kate n0 is still an eigenstate of the unperturbed Hamiltonian H0 with the same eigenvalue, which is given by E0. That means we are having this equation kate psi naught. It's a general state which can be written as a linear combination of kate m0 and kate n0. But then you can show that the unperturbed Hamiltonian acting on kate psi naught is actually going to give you the same energy eigenvalue and kate psi naught back. This we have already seen. Now we also have said that typically the perturbation will lift the degeneracy. That is another aspect of degenerate perturbation theory. Perturbation will lift the degeneracy. In fact, this happens in many scenarios, but it may not happen also that the perturbation leaves the degeneracy in the first order. But we are not going to discuss this in this class. So what I wanted to mean is that as you increase lambda, your perturbation parameter lambda, remember your total Hamiltonian was H0 plus lambda H1, where H1 was your perturbation Hamiltonian and lambda was the parameter that you had introduced in order to keep track of orders in the perturbation. So as you increase lambda from 0 to 1, the common unperturbed energy E naught, that actually splits up into two, because we have here twofold degeneracy, and if we plot, what we will get here is the following. Suppose this is the value of your unperturbed energy E naught. Along this you are having E lambda, along x axis you have lambda, and you already know that lambda can take values from 0 to 1. So what this says is that you can have something like this after you have introduced your perturbation. What happens when we turn off the perturbation? That is another question. What happens when we turn off the perturbation? That's another question which you might be eager to know. See, what happens here is that this upper state, whatever it has split into, reduces to one linear combination of Kate M naught and Kate N naught, and the lower state reduces to some orthogonal linear combination of them. So that's what actually happens. But we don't know a priori what these good combinations are. So we really do not know what the real good combinations or linear combinations are, and for this reason we cannot even calculate the first order correction to energy, because calculation of the first order correction to energy requires knowledge of the unperturbed state, and we do not know what unperturbed state to start with. So that's the real problem in degenerate perturbation theory, that we have already mentioned in the general discussion of degenerate perturbation theory. When we had this discussion in the previous two lectures, we had mentioned this, but for this particular example of two-state system with twofold degeneracy, we are seeing this explicitly. Now, therefore, for the moment, let's just write the good unperturbed states like the way we have written here. Let us number these equations. Suppose this is equation 1, this is equation 2. So to start with, let us actually just write the good unperturbed state as we have written in equation 1, and keeping these alpha and beta to be adjustable. That means that we are not fixing the alpha and beta, because we do not know a priori which alpha and beta to start with. So we are keeping the most general form. And then we go on calculating or solving this problem. That means we need to solve, as always, you need to solve Hi equal to E psi. This is the Schrodinger equation, with your H being given by H naught plus lambda times the perturbation Hamiltonian, where H naught is the unperturbed Hamiltonian. And of course, you know that we have expanded the Kate psi and the energy E in lambda. So this will be like E naught plus lambda times first order correction to energy plus lambda square times the second order correction to energy, like this. And also our Kate psi will be Kate psi naught, the Kate which we have written here as in equation 1, the unperturbed Kate, plus lambda times the first order correction to the state Kate plus lambda square times the second order correction to the state Kate, and so on and so forth. Therefore, I am not going to elaborately discuss this, because we have done this several times by now. You need to substitute these two expansions back into this equation Hi equal to E psi, and what you are finally going to get is that H naught Kate psi naught plus lambda h1 ket psi naught plus h naught ket psi 1 plus higher order terms in lambda is equal to E naught ket psi naught plus lambda first order correction to energy times unperturbed state ket plus E naught unperturbed energy times first order correction to the state ket. And then of course higher order terms in lambda. That's what you are going to get. That means we are just writing this equation up to order lambda. Then you give the argument that you have to collect the different powers of lambda coefficients, and you finally obtain at equations like this when you collect the coefficients of order lambda to the power 0 term. That gives you the standard unperturbed Schrodinger equation. Then if you collect the terms up to order lambda to the power 1, the coefficients of terms up to order lambda to the power 1, there you get h naught psi 1 plus h1 psi 0 is equal to E0 psi 1 plus E1 psi 0. Now let us number this equation as 3, and then what you do is that you take this equation number 3 and take the inner product with bra m naught. So you take this equation and take the inner product with bra m naught, and what you get is m naught h naught psi 1 plus m naught h1 psi 0 is equal to E naught m naught psi 1, because E naught is a number, E1 is also a number, so we will have E1 m naught psi 0. And immediately, because h naught is Hermitian, this acts on m naught to gives you E0 bra m naught. So this is going to give us E0 or E naught bra m naught ket psi 1. And this is plus m naught h1 psi naught equal to E naught m naught psi 1 plus E1, because m naught psi naught. Now because this E naught m naught psi 1 are on the both sides, they cancel, and what we finally arrive at is m naught h1 psi naught. This matrix element is equal to the first order correction to energy times the inner product of m naught with psi naught. Remember, this psi naught was the linear combination of the states m naught and n naught, which are degenerate. So here what you explicitly do is that substitute equation 1. The equation 1 was this first equation which wrote this ket psi naught in terms of the two degenerate states m naught and n naught. So if we substitute equation 1 here, what we are getting is m naught h1 alpha m naught plus beta n naught is equal to E1 m naught alpha m naught plus beta n naught. So if we simplify this, what we are left with is alpha m naught h1 m naught plus beta m naught h1 n naught. This is equal to alpha times E1 This is our equation number 4. Why alpha times E1 only? Because this alpha is a number, so it will come out, and what will remain here is m naught inner product, and the second term there will be m naught n naught inner product, but because of orthogonality m naught n naught inner product is going to give you 0. So this is one equation which we can write in terms of the matrix elements as alpha. This object here is nothing but H1 mm, the mmth matrix element of the perturbation matrix H1, plus beta H1 mn, which is equal to alpha E1. So this is one of those important equations which we will see later that how it can be used. So here we have used the notation H1 Ij is I naught H1 J naught. Again, as always, this 0 represents unperturbed states, and of course Ij can take values m and n only. Similarly, if you start with this equation number 3, and instead of taking the inner product of this equation number 3 with bra m naught, now if you take the inner product with respect to bra n naught, then you will get another equation exactly like equation number 5, and that equation will look something like this: alpha H1 nm th matrix element, beta H1 n nth matrix element is equal to beta times the first order correction to energy. This is what you are going to get when you take the inner product. So inner product with respect to bra n naught. So this, how do we get this equation? Take inner product of equation 3 with n naught and follow the exactly same procedure that we have followed in order to get equation number 5. You will arrive at this equation. Now, first important note is the following: H1 Ij are in principle known. They are just the matrix elements of the perturbation matrix H1 with respect to the unperturbed states, of course, m naught and n naught. It is a different question whether we know the exact linear combination, that is whether we know alpha and beta. That is a different question, but the states m naught and n naught are known. So now what we do is that we multiply this equation number 6 by H1 mn. Okay, so multiply 6 by H1 mn, and then we have to use equation number 5 to eliminate a term which is beta H1 mn. If you do this simple step, the equation that you arrive at, let me show one calculation, the next part you can do. So I have multiplied equation number 6, this equation by H1 mn from left. Okay, so alpha H1 mn, then we have H1 nm plus beta H1 mn H1 nn is equal to beta E1, both of them are number, and then H1 mn. We can write this as alpha H1 Mn H1 Nm plus, now here we have to replace this beta H1 Mn using equation number 5. So beta H1 Mn from equation number 5 is nothing but alpha E1 minus alpha into H1 mm. So we just write that. So we write this as alpha E1 minus alpha H1 Nn times H1, I think I made a mistake here. This was H1 Mn in terms of mm. Okay, so this should be m here, and then this should be n here, and then this is equal to alpha E1 minus alpha H1 mm multiplied by E1. This we have found using equation number 5, replacing beta H1 Mn by alpha E1 minus H1 mm. So now this can be written as even more in a simplified form. Alpha, we can take alpha altogether common from all these terms. Then what will remain is H1 Mn, H1 Nm, and then if I take everything to the left hand side, we will have terms like E1 minus H1 mm into E1 minus H1 Nn. This equal to 0. So that's what the equation will give us. Now if alpha is non-zero, if alpha is not equal to 0, then this equation, let me number this equation number 7. Then equation number 7 yields an equation for the first order correction to energy E1, and it's a quadratic equation. That's what you would have guessed. We have done this already, and let us write down this quadratic equation. This is going to give us E1 squared minus E1 H1 mm plus H1 Nn plus H1 mm H1 Nn minus the cross terms H1 Mn and H1 Nm is equal to 0. So we will get two different values of energy as expected, and as you have already seen when we discussed the near degenerate system. So this is going to give us E plus minus first order correction, two values of energy, and that's what we have already tried to derive once for nearly degenerate systems. So this is going to give us mm plus H1 Nn plus minus square root H1 mm minus H1 Nn whole square plus 4 times mod of H1 Mn whole square, keeping in mind that H1 Mn and H1 NM, they can be complex conjugate of each other. And this is basically the equation that I have written here. This is basically the fundamental equation of degenerate perturbation theory. Let us write this equation number 9. And the two roots corresponding to the two perturbed energies are given by this equation, E1 plus minus. But now you ask the question, we have selected this for alpha not equal to 0. But what if alpha equal to 0? That also is another possibility, that alpha equal to 0. Now if alpha is equal to 0, then immediately what was alpha? Alpha, you remember, you have written down your unperturbed state as a linear combination of your original degenerate states, alpha m naught plus beta n naught. Now if your alpha is equal to 0, this immediately implies your beta should be equal to 1. And in that case, if your beta is equal to 1, then let us look at this equation number 5. Alpha is equal to 0. That means H1, so from equation number 5, H1 mm and alpha E1, these are 0. Therefore, H1 mn equal to 0. So this implies from equation 5, H1 mn equal to 0. Similarly, equation number 6, if you look at, we get immediately my alpha equal to 0 means H1 nn equal to E1. So equation 6 gives us H1 nn equal to the first order correction to energy. This is actually included in this general result that I have written. Very carefully you note that with the negative sign, if you choose the negative sign here, this exactly is included. Whereas the plus sign corresponds to alpha equal to 1 and beta equal to 0. What is more, that the answers that E plus first order correction to energy, which is H1 mm, which is nothing but m naught H1 m naught, and E1 minus, which is H1 nn, which is n naught H1 n naught. These two answers are precisely what we would have obtained using non-degenerate perturbation theory. So we have been kind of, I should say, very lucky. The states Kate m naught and Kate n naught were already the good linear combinations, and obviously it would be, I should say, greatly to our advantage if we could somehow guess the good states right from the beginning. Then we could go ahead and use the results of non-degenerate perturbation theory. In fact, as I already have mentioned, that one can take help of this following theorem. Let me state the theorem for you again. This theorem, we said that suppose omega be a Hermitian operator, and omega commutes with H naught and H1. Now, if m naught and n naught, which are the degenerate eigenstates of H naught, are also eigenfunctions of omega, if m naught and n naught are also eigenstates of this operator omega with distinct eigenvalues, they cannot be the same. The eigenvalues must be different. That means when omega acts on m naught, suppose it gives us mu m naught, and when omega acts on n naught, it gives us, say, eta n naught. And explicitly mu is not equal to eta. Then you can clearly say H1Mn equal to 0. And hence N0 and M0 kets are the good states to use in perturbation theory. That makes your life so much simple, and the proof you already have seen. So we said that our assumption was omega H1 should be equal to 0, and if we look at this matrix element m0 omega H1 commutator with n0, then we know that immediately it is 0 because this commutator is 0. But if we break this, we will have terms like m0. The first term of the commutator will give us omega H1 n0 minus m0 H1 omega n0. And this we can write as omega m0 and H1 acting on n0 minus, we can also write this as m0 H1, and I know what omega acting on n0 gives. It gives eta n0. So eta is a number, it comes outside. And also similarly, omega acting on m0 gives us mu m0. So this gives us mu minus eta m0 H1 n0. And of course this is nothing but mu minus eta H1 mn. Omega acting on m0 gives us mu m0. That's what we have used in this step. But we already have said mu is not equal to eta, therefore H1 mn must be equal to 0. So the moral of the story is that if you are faced with degenerate states, you must look around for some Hermitian operator omega that commutes with both H0 and H1. Pick as your unperturbed states the ones that are simultaneously eigenfunctions of H0 as well as omega, and then use the ordinary perturbation theory. If you cannot find such an omega, then you have to use this general result which we have written here in equation number 9. Now, of course, you will ask that fine, we are happy with this twofold degeneracy. What if there is n-fold degeneracy with n greater than 2? So far all our discussions are limited to twofold degeneracy. In fact, I have shown this what happens if we have this capital N-fold degeneracy. So let us denote this by capital N-fold degeneracy. That discussion was already done. So it is easy to see now that how this method can be generalized. What you do is that you write down this, you take these equations 5 and 6. Take this equation 5 and equation 6 and write these two equations in terms of a matrix form. That means take 5 and take 6. Take 5 and take 6. And I can always write this equation as H1 mm H1 mn H1 nm and H1 nn. This is a matrix, and then there is alpha beta and then there is E1 and alpha beta column vector. You can always do that. So take this 5 and 6 equation numbers, and we can write this in like this matrix form, and this is nothing but an eigenvalue equation for H1, isn't it? That's what you can immediately see. This is nothing but an eigenvalue equation for the perturbation matrix H1. And E1s are the eigenvalues of this H1 matrix. And then equation that I have written here, equation number 8, is the characteristic equation for this matrix, and good linear combinations of the unperturbed states are the eigenvectors of H1. Eigenvectors of H1. So to generalize, in the case of capital N-fold degeneracy, we look for the eigenvalues of the n cross n matrix. So to generalize, in case of n-fold degeneracy, you need to look for the eigenvalues of n cross n matrix, which is given by H1 Ij is equal to I naught H1 J naught. That's it. Finding the good unperturbed eigenfunction amounts to constructing a basis in the degenerate subspace that diagonalizes this matrix H1. Once again, if you can think of the operator omega that I have just introduced here, if you can think of such operator omega that commutes with H1 and use the simultaneous eigenfunction of omega and H naught, the unperturbed Hamiltonian, then the H1 matrix will automatically be diagonal. That's what it says, because there is no diagonal element. H1 Mn is 0. So if you find such operator omega, then this H1 matrix will automatically be diagonal, and you will not have to complicate your life with the higher order characteristic equations in case of your degeneracy is much more than 2. Okay, fine. So let us apply this thing. Let us apply this thing to a concrete example, and the example is the following. Consider an infinite three-dimensional cubical well which is given by 0 if we have the limits x is between 0 to a, y is between 0 to a, and z also is between 0 to a. The potential is 0 and it is infinite otherwise. That's your unperturbed potential. So you already know what are the wave functions for this system, because you have already discussed the three-dimensional cases. So in your PH 204 course. So what are the wave functions? Nx, ny, nz. There will be 3 different quantum numbers, and this is the unperturbed wave function. This will be the functions of x, y, and z. So remember, we had the square root 2 by a sine n pi x by a is as your one-dimensional wave function for an infinite well. Here it should simply be 2 by a to the power 3 by 2 instead of half, sine nx pi by a into x, sine ny pi by a into y, sine nz pi by a into z. That's what your wave function is, and these nx, ny, nz's, they are all positive integers starting from 1. Now hence you also know the unperturbed eigenenergies, right? So unperturbed eigenenergies are all E nx, ny, nz. We denote this 0 to denote that we are dealing with unperturbed eigenenergies, and this is equal to pi square h slash square by 2m a squared nx square plus ny square plus nz squared. Now, of course, the ground state is non-degenerate. Ground state is non-degenerate because ground state is denoted by psi 1 1 1. That means nx, ny and nz are all having the same value, and you already know what this is. The ground state energy is nothing but therefore 3 pi square h bar square by 2 ms square, because all nx, ny and nz are all 1, therefore this gives you a contribution of 3, and this is 3 pi square h slash square by 2 ms square. But the first excited state is triply degenerate. Now we don't have n equal to 2, rather we have n equal to 3, triply degenerate. Ab aayega maza. So triply degenerate state, we have different values of nx, ny, nz. Let us denote them by, so suppose this is psi a, psi b and psi c. So what is psi a? Psi a means this is psi 1 1 2, because nx can be 1, ny can be 1 but nz can be 2. Similarly, psi 1 2 1 is psi b, that means nx can be 1, ny can be 2 and nz can be 1. And psi c is 2 1 1, that means nx can be 2, ny can be 1 and nz can be 1. See, all these are combinations of different 1s and 2s, but when they combine, they give you this value for nx square plus ny square plus nz square to be equal to 6. So for all these different states, we will have the single value of energy, unperturbed energy, E20 is 6 pi square h slash square by 2 ma square, or 3 pi square h slash square by ma square. That's where the states, these three states are degenerate, meaning they have the same value of energy E20. Now, at this stage, you introduce the perturbation. Introduce a perturbation of this following form. It will be a constant perturbation, and the form of the perturbation is the following. Let us write this as V naught, which is a constant. So this V naught is there between 0 and a by 2 along the x-axis, 0 and a by 2 along the y-axis, and it is 0 otherwise. So that's what my perturbation is. Now how does this thing look like? So it will look something like this. Then let me join this. And suppose this is my, okay, first let me draw the x, y and z axis. So this is my y axis, this is my x axis, and this is my z axis, and these are the middle parts a by 2 for x and y axis. So this is a, this is a, this also is a along z direction, and this is a by 2, this is a by 2. So there is a constant thing. So what we can do is that we can now draw this maybe with a different color. Yes, that's it. So we have this perturbation sitting here, which is nothing but a constant perturbation. So this region which I am putting this shade on is the perturbed region. So this raises the potential by an amount of V naught in 1/4 of the box. So that's what is important. It actually raises the box by 1/4. It's exactly like the same thing when we actually raised the base of the half of the base of the one dimensional potential well, but now we are doing this for 3 dimension. So that's my perturbation for you. Now of course if you try to calculate the ground state correction, first order correction to ground state energy, then immediately you know what it is. It's nothing but E11, and the states are just psi 111 and then H1 and then psi 111. So that's it. So this you need to evaluate, and you know very well how to do that. We have done this several times. 2 by a whole cube V naught. Now this perturbation is there along x axis, so there will be sine square pi x by a, because nx is 1 dx, into along y axis of also this is for 0 to a by 2, so this is sine square pi y by a, ny is equal to 1 also, dy, and into, but now along z direction this is from 0 to a, 0 to a, sine square pi z by a dz. That's it. So if you evaluate this, I am not doing this, evaluate this thing, this is just sine square theta d theta integration. 2 by a whole cube V naught will be there, and 0 to a by 2, if you integrate this you will get a by 4. This will also give you a by 4, and this is going to give you a by 2. So we will have a cube by 32. So that will cancel one a cube from the denominator and numerator, and it will just be having V naught by 4. But isn't that what you expect? This is pretty much what you would have expected. The potential is raised by this constant amount V naught in 1/4 of the box, and that's what exactly is shown up in your ground state energy. Now for the first excited state, we need full degenerate perturbation theory. First excited state calculation, we need fully degenerate perturbation theory, and for that First you note that the diagonal elements of H1 are the same as the ground state. So H1AA is equal to H1BB is equal to H1CC, all are basically V naught by 4. So the diagonal elements of this matrix is fine. So you have to construct this matrix H1 and the diagonal elements are just nothing but V naught by 4. The off diagonal elements of course are much more interesting. So for off diagonal elements, for example, you want to calculate H1AB. What should be H1AB? Remember we were writing this ABC to denote these three different states. So now what is H1AB? H1AB, if you want to evaluate, you do this 2 by A cube V naught. So from 0 to A by 2, we will have sine square pi x by A dx, and then we will have 0 to A by 2 sine pi y by A, and then sine 2 pi y by A dy, and then it will be sine pi z by A sine 2 pi z by A dz. But this 0 to A sine pi z by A sine 2 pi z by A, if you evaluate, this is going to give you 0. Therefore this whole integral is 0. Exactly by the same reason, if you try to evaluate H1AC, then there also will be a term exactly similar to this sine pi z by A into sine 2 pi z by A from 0 to A. That will also give you 0. So that H1AC will also be 0. The only non-zero contribution will come from H1BC. So this is 2 by A whole cube V naught, and then 0 to A by 2 sine pi x by A sine 2 pi x by A dx into sine 2 pi by A into y sine pi A y by A into dy. This also is from 0 to A by 2, and then we will have sine square pi z by A dz from 0 to A. This is not going to be 0. In fact, if you evaluate, this is going to give us 8 V naught by A cube. This first term is going to give us, please check this, this is going to give us 2A by 3 pi. Second term also going to give us 2A by 3 pi, and the third term is going to give us A by 2. And therefore this is finally going to give you 16 V naught by 9 pi square. That is your answer for H1BC. Now your matrix is fully done. So you know what your H1 matrix is. H1 matrix therefore is nothing but, you know, its diagonal elements are all V naught by 4. So take this V naught by 4 common, and your diagonal elements will all be 1, 1 and 1. And then you have just seen that your HAB and HAC, those are 0. So this is 0, this is 0, this is 0 and this is 0. But your HBC is non-zero, so that gives you some kappa here, and kappa, it's not 16 V naught by 9 pi square because we have some V naught by 4 outside, so it will simply be that means kappa times V naught by 4 is your 16 by 9 pi square into V naught. So that will give you your kappa to be it should be 64, so 8 by 3 pi whole square. So your kappa is 8 by 3 pi whole square, which numerically it's constant and its value is roughly around 0.7205. So what should be the characteristic equation? The characteristic equation In order to figure out what are the correction to energies, we need to solve this characteristic equation for not for H1, rather for H1 into 4 by V naught. That would make our life easier. So if we want to evaluate this characteristics equation, that means we need to write this as determinant 1 minus say delta 0 0 0 1 minus delta, then there is kappa 0 kappa 1 minus delta is equal to 0. And this immediately will tell us we have 1 minus delta here, and then 1 minus delta whole square minus kappa square is equal to 0. This immediately gives us the solutions for the eigenvalues. Delta, one value of delta will be 1. This is from this. Delta 1 equal to 1. And then another will come from this equal to 0. That means 1 minus delta is equal to plus or minus kappa. So this means delta should be 1 minus plus kappa. So let us call this delta plus minus, or maybe so. Okay, let us write the 3 distinctly. Delta 2 is equal to 1 plus gamma, 1 plus kappa, and this is nothing but 1.7205, and delta 3 is 1 minus kappa, which is 0.2795 roughly. Therefore, to first order in lambda, what we are getting is this: E lambda is equal to E20 plus lambda into V naught by 4. Then we have E20 plus lambda into 1 plus kappa into V naught by 4. And the third one is E20 plus lambda into 1 minus kappa into V naught by 4. Okay, so these are the energies, and you can see that this first order correction to energy, they all have this first order correction to energies, they all have been lifted the degeneracy. So this has been the feature of this problem, that if I start with some value of say E20 somewhere here, which by the way we know from the unperturbed case, then we immediately see that there is a lift of degeneracy like this. So what we get here is this, that we have different values: 1 plus kappa V naught by 4, this is your original V naught by 4, and this is 1 minus kappa V naught by 4. Okay, so this is your E as a function of lambda versus lambda. So this E20 is the common unperturbed energy. The perturbation has lifted the degeneracy, and it has splitted the level E20 into 3 distinct energy levels. And now note that if we had applied non-degenerate perturbation theory naively to this problem, we would have calculated that the first order connection to the energy is the same for all 3 states, and which is equal to just V naught by 4, which is actually correct for only one state, which is in the middle. But it is not correct for the other 2 broken states, where the degeneracy has been lifted. Now, meanwhile, the good unperturbed states are the linear combination of this form, as I have already said. So what should be the good unperturbed state for this? This should be alpha psi A plus beta psi B plus gamma psi c, because remember the psi a, psi b, psi c are the unperturbed levels, unperturbed degenerate states to start with. They all had same values of the energy, same value of the eigenenergy. So we know that this can be a good combination, and these coefficients alpha, beta and gamma, these need to be figured out. So we have this matrix 1 0 0 0 0 1 kappa kappa 1, and then we have this alpha beta gamma, and this is equal to our the eigenenergy delta alpha beta gamma. That is the equation that we need to solve for delta equal to 1 and delta equal to 1 plus minus kappa. So let us take delta equal to 1. If we take delta equal to 1, we get this, right? So alpha is equal to 1, because if we take delta equal to 1, then we will have this 1 into alpha plus 0 into beta plus 0 into gamma is equal to delta into alpha, but delta is equal to 1. So your alpha equal to alpha is one equation. So alpha equal to alpha, and then beta plus kappa gamma is equal to beta, and gamma beta, sorry, not gamma beta, rather it's kappa beta plus gamma is equal to gamma. So this immediately implies beta equal to 0. This implies kappa gamma equal to 0. That means gamma equal to 0. And this implies alpha equal to 1. In this manner, if you try to again choose delta equal to 1 plus or minus kappa, then you will end up with two different sets. One is alpha equal to 0, beta and gamma equal to 1 by root 2. Another one is alpha equal to 0 corresponding to 1 minus kappa, beta is equal to minus gamma, which is equal to 1 by root 2. So your good states will be psi a, or let me write this psi 0 as either it can be psi a, it can also be 1 by root 2 psi b plus psi c, and it can also be 1 by root 2 psi b minus psi c. So this is corresponding to your alpha equal to 0, alpha equal to 1, the first case when delta is equal to 1, gamma and beta are 0. Similarly, this is corresponding to your alpha 0, then there is no psi a part in this combination, and beta gamma are 1 by root 2, it's normalized, and this corresponds to again alpha 0 and beta equal to minus gamma equal to 1 by root 2. So these are the different combinations that you will get. But now let me tell you one thing. These results, can you have guessed by noting that there exists an operator which will commute with H1? If you can guess that, then this whole calculation would have been even simplified than this. So think about whether there exists such an operator which will commute with H1, and thereby by the theorem that I have mentioned here, by the theorem that I have just mentioned here, this one, you can actually apply your non-degenerate perturbation theory result and calculate the final result that we have calculated after solving this characteristics equation. So